Uh, okay. There's also another thing that fascinates me, which are known as Maxwell equations. And we're going to use these Maxwell equations and we're going to drive a wave equation from them. Uh, so to get started with, so we're going to look at these Maxwell equations first. We're going to look at these laws that is right on the left of the page, which says the first law says, which is actually a Gauss's law, uh, that says that the divergence of your magnetic flux electric flux density is equals to volume charge density. What that means is that you need to remember something about electric charges is that they start from a charge and they end from on the charges, and this thing would become zero. So we're saying this: the charges are you have let's say you have two charges. So electric field starts from a charge and ends on a charge, and if I were to find out what is the total charge enclosed, I will take a volume of that, and I will integrate with respect to volume. This is what that means. And this is actually coming from Gauss's law. If I have a charge free region, this PV rho V, which is actually defining volume charge density, that would become zero, and we're going to assume that to drive wave equation. The second law is also known as this is a Gauss's law for magnetic field, which says the divergence of your magnetic flux is equals to zero. What that simply means is that you need to remember something about magnetic field is that they are closed loop lines. What I mean to say they are closed loop lines, they go, if you think of a magnet, it goes from north to south. So they are closed loop line. That's why there is a zero there. Now, these are the two equations which I'm really interested in, which are known as Faraday's law. That a change in magnetic field will produce a change in electric field will produce me a change in magnetic field with respect to time, and change in magnetic field will produce me a change in electric field. That is with respect to electric flux density, as you can see. So we're going to use these four equations, and we're going to try to derive wave equation from them. So in order for me to do that, they are already in time domain right now. I would like to do them in phasor domain. So the first thing I'm going to do, I'm going to convert these Maxwell equations in phasor domain. All right, my pen is not working. So the first thing we'll do, so the first step is, convert them in phasor, which means I want to look at these equations in terms of frequency domain. Okay, these two I really don't care about. Why? Because these are for electrostatic and magnetostatic. These two definition I'm really interested in. Why? Because this tells me something about dynamic fields, and I can replace that. So the first thing I'm going to do, I'm going to pick up this equation on my left hand side. So I'm going to write this down. The curl of electric field. I'm not going to change it to phasor yet. And as we know, d over dt, that can be changed. So d over dt in phasor domain can be replaced with j omega. So this is the first identity I'm going to do, sort of like an identity, or there's a small proof for it too, but we're just going to use that we're going to replace d over dt with j omega. Okay, so when I replace this with j omega, this would become negative j omega. I know B, there's also something else that I know about B. B is magnetic flux, which is given by mu times H. So I'm going to make that replacement as well. So I'm going to make that replacement in place of B. So d over dt has been replaced by j omega. And I'm going to make a change. B is going, I'm going to replace this with mu times H. So this is going to be mu times H. So when I change that, now I'm going to change that into a phasor form, and I'm going to use that tilde symbol to represent that it's in phasor form. All right. So this is that first equation. Now for the second equation, what I'm going to do exactly the same thing. The curl of a magnetic field, I'm going to replace that in a phasor domain. The curl of that magnetic field is J, which is conducting current, which is introduced by Maxwell, plus this d over dt can be replaced with j omega, and d, which is also I know D is given by epsilon times E. I'm going to make that replacement as well. So this would become epsilon times E. What else you need to know about epsilon here and mu is this. Mu is actually mu times mu r, and epsilon is epsilon naught times epsilon r, where mu naught and E naught, these are the constant, and mu is the relative permeability of a material, and epsilon r is relative permittivity of a material. What permittivity and permeability is how much that material is polarizable in terms of electric component, in terms of electric field and magnetic field. So once I do that, now I have these two equations with respect to phasor domain. Now the next thing that I want to do is something is this. What I'm going to do is this, that I'm going to make this replacement. I know something else about J. I know something else about J. J is conduction current, which is Joule's law, which says the current or the conducting current is equals to the conductivity of a material times what is it? Conductivity of a material times electric field. This is Joule's law. All right. This is Joule's law. All right. So I'm saying this. This is your conduction current is equals to conductivity, how easily electrons can flow in a particular material, times electric field. So when I think of this, this is sort of like an Ohm's law version of for electric field. So if you were to look at your Ohm's law is equals to V is equals to IR. This is for circuit analysis that we normally use. V is equals to IR. Exactly the same thing for electromagnetic. Why? If I replace this J, if this is conduction current, I can simply replace with I. And I know conductivity is an opposite of resistance, which is 1 over R. And I know electric field can be easily replaced with voltages. So this is actually becomes I is equals to V over R, which is just like Ohm's law. So Joule's law is a similar thing as Ohm's law, but for electromagnetic analysis. When we're doing electromagnetic analysis, that's the law that we like to use. So I'm going to make this a replacement here on this side. So once I make that replacement here, so this would become, so this equation, this particular equation would become something like this. Is going to be omega times conductivity plus j omega epsilon times E tilde. This left side would become this. What did I do here? In place of j, I made this placement. So let's do this step again in a different way. So instead of j, I'm going to rewrite this equation here. So I'm rewriting this equation here. So j is conductivity times E plus j omega epsilon E. So I took out the common, which is your electric field. So once I take this out, I'll end up with this equation. All right. Once I take this out, I can also write this equation in a different way. I can also write this as a different way. I can write it like this. I can write this as j omega times epsilon minus j multiplied by conductivity divided by omega times E tilde. So how do I do that? So this is exactly the same thing. I've just taken out a common. Look at this. So when I multiply j omega by j omega, all right, this would become j omega E. And I also know something, that j omega j squared is equals to -1. That -1 and -1, so j squared is -1. So when I took that j out, this j and j would become -1. That's why your sign has changed from positive to negative. All right, that's why your sign has changed, and you get this term, which is omega conductivity divided by omega. I hope you're seeing this step. What did I do? I took j omega out, j omega multiplied by E, which would give you exactly this term, and j omega and j omega, that sorry, not j omega, just j squared it's actually -1, and so that's why the sign has changed. And then you have conductivity, which was part of this, divided by omega. So when I multiply this by this would get a -1, and then omega omega will cancel. I will get exactly the same thing back. So this is the replacement, and I'm gonna call this guy. I'm gonna call this guy epsilon c, and this thing has a name which is known as complex permittivity. I hope you're following the steps. If not, please let me know in the comment section. All right. So now this equation, this particular equation right here, this equation has become curl of an H is equals to J omega epsilon C times E. All right. So J omega epsilon complex permittivity times electric field. So this has become transformed into this. So once I have these two equations in, now I'm ready to play around with them and try to convert them into something called wave equation, which is normally given in the books and stuff like that. You can also look at your electromagnetic book as well. So the next step is this. Okay, so the first thing I'm going to do, I'm going to pick up this equation on top. So now these were the preliminary steps that we were doing. We're going to pick up this, and we're going to pick up this, and we're going to start solving this. Okay, so I hope you guys are seeing it. So I'm going to start from here. Okay, so the first step I'm going to do, I'm going to pick up this equation, which is curl of an E is equals to negative J omega mu times H. All right. So what I'm going to do, I'm going to take a curl of both sides. So when I'm taking a curl of both sides, I'm going to take a curl of this side, I'm going to take a curl of this side. When I do that, I'll end up with this equation on my left hand side. I hope you guys are seeing it. By is equals to, now what this equation would become, this would become, so what I'll do is this, when I distribute among these are just constant term, negative J omega mu, these are just constant terms, so I'm going to simply take them out. I'm going to simply take them out, and I'll end up with this curl of an H. But I already know something about curl of an H. Curl of an H, which is right here, isn't it? Curl of an H is right here. So I'm going to make that substitution here. So this is going to be negative J omega mu. Curl of an H is J omega epsilon C times E. Where am I coming up with this? This curl of an H, we already solved for this in phasor domain, which is this. So I'm just simply making that replacement. So I know something else too. So J, imaginary J is a squared, and J squared is -1, so this will change into positive. So I'll end up with, and then this would become squared. So this is going to be omega squared. Then this would become mu times epsilon C times E tilde. I hope you're seeing this step. So J and J, that is a squared, and J squared, I already know this is -1. So -1 and negative, that would change that into positive, and you will end up with omega squared mu times EC times E. All right. Now the next step is this. I know something else. There's also an identity, which is a vector identity that I'm going to use here, that says, there's a vector identity which says that if you have a vector and you're taking the curl of that vector, you can replace that with del operator multiplied by del dot E minus del squared E. So this is that vector identity that I'm going to use on the left hand side. All right, so this is that vector identity that I'm going to use at the left hand side. There's also something else that we also know. What is del squared? Del squared of any vector is actually given by a partial derivative with respect to x plus partial derivative with respect to d of y, partial derivative with respect to d2z. Is basically a second order derivative, partial derivative, which is this. So basically it's representing some type of a change. All right, so this is just some extra information that is there. For rectangular coordinate, that's what it is, and for spherical and for cylindrical coordinate is different. So this is normally there in any electromagnetic book. You can look at it in terms of an identity for this. So the first thing I'm going to do is this. Now if I were to look at this particular vector, what else do I know? All right, if I have a charge free region, so let me write this down. Let me write this down over on this side. So this is going to be, I just gotta be careful because I don't want to get trolled. Minus del squared times E. Okay, I know something about this. So I'm just simply replacing that with an identity that I'm using it, which is right here. Okay, I know something. What is del, divergence of an electric field? I know that divergence of an electric field, when it's a charge, when there is a charge on a region, it's actually PV. But what about if it's a charge-free region? Then this, if it's a charge-free region, that del of E would also give me 0. There is no charge present on the surface. So I'm going to make that assumption, and I'm going to cross this out, and I'm going to make that 0. So I'll end up with this whole thing going to 0. So I'll end up with negative del squared E so I'm going to end up with negative del squared is equals to omega squared mu times E times E. All right, and I can rewrite this equation as, so this equation, I'll just move it on the other side. I'll end up with this equation. Del squared, I'll simply move this on the other side. Simply, I'm just moving this equation on the other side. So this is going to be simply moving this and making it equals to 0 would give me plus omega squared mu times epsilon c is equals to 0. I'm not doing anything fancy. I just simply move this on the other side, make this whole thing equals to 0. So I'll end up with this first equation. All right. I hope you guys are getting it. Okay. Now, there's also one more replacement that I can do. I can say I have gamma squared. Let's introduce something called gamma squared. Gamma squared is known as complex propagation constant. So what I'm going to do, I'm going to say this gamma squared, which is complex propagation constant, is actually minus omega squared mu times epsilon c. All right. What I'm going to say is this. My gamma squared is going to be minus omega squared mu times epsilon c. This is the replacement I'm going to make. So this, my first equation would look something like this. Now this will change. I got to write it in with a different pen so it looks nice. All right. So let's do this. So let me use a fountain pen. So now this would change into del squared minus gamma squared. I'm making this replacement, minus gamma squared times E is equals to 0. Very important equation. I end up with first equation. All right, and this is a wave equation for E. For E. All right. Now, if I were to redo that process again, and if I start from this equation and I redo that again, and I start doing the same process again, I will also come up with the other equation, which is known as wave equation for your H. If I do the same process, but instead of doing it with E, if I were to repeat that same process again, I would end up with an equation which is known as del of H minus gamma squared H is equals to 0. Now this is your wave equation for H. All right, very very important equation. So this is how you normally drive wave equation using Maxwell equation. And why am I calling it a wave equation? uh, let's do this comparison in the next video, but I think I already made this video so long. So I hope you like the video. If you have any questions, leave it in a comment section. uh, uh, and don't forget to subscribe to the channel.